Microphone. Yeah. So, okay. Thanks, Jens, for the introduction. And as Jens said, I already accepted the award once, so I accepted twice. Thank you very much. Thanks to the committee, to the whole community for this award. I really greatly appreciate it. I have tremendous appreciation for the programming languages community. Now, the purpose of today's lecture, however, is to, convince you that the answer to the question that you see there on the slides is yes. Okay? And in some sense, I believe that the time is right for us to start looking at some of these problems that I'm going to be talking about, some of these challenges. And so the talk is not so much a retrospective talk about what I did with my collaborators over these 10, 12 years, or 20 years since PhD, but about new problems that I believe we can work on together. And so let's begin. I don't know if this will work here, but so as you know, deep learning has revolutionized entire areas, disrupted entire industries, and is continuing to do so. From autonomous driving, healthcare, medicine, natural language processing, game playing, and many more. And this is thanks to a number of, start the timer. You don't have to start it, it's fine. It's thanks to a number of great technical advancements developed over the last 10 to 12 years, built on top of other advancements the decades before. Now, despite this amazing progress, there are some fundamental, some key problems that we start to increasingly see with deep learning techniques and methods. All right. So here's some of the problems. These models, these methodologies need too much label data to learn basic concepts. It's not really how people learn. They don't generalize well to slight shifts in distribution, so slight distributional shifts. Lack obvious robustness, safety guarantees, reasoning abilities, background knowledge. Learning basically starts as soon as a new data set comes basically from scratch. A lack of reasoning ability, especially causal inference, and many other problems. So, next generation learning systems, whether you want to call it deep learning 2.0 or AI 3.0 or something 4.0, it doesn't matter. They have to address some of these issues. Otherwise, we're going to end up in another winter, which is not so great. Now, there is some consensus in the community that some breakthroughs are needed, like the time is right. So for instance, Hinton, who won the Turing Award a couple of years ago with Jan LeCun and Joshua Bengio, says we don't need all this label data. The future depends on some graduate student who is very suspicious of everything I've said, or maybe a Popov researcher. I don't know. And Judea Por, who won the Turing Award in 2011, says he's extremely impressed with what deep learning has done, but it essentially amounts to basically curve fitting. And he's just surprised that curve fitting can solve so many problems. But he's asking, what's next? So what's next? The community is open to new results, to some breakthroughs that somehow look like they have to take place, because otherwise we'll be stuck with, running more and more GPUs and waiting around. So here's the fundamental question for us in this community. Can programming language research impact deep learning 2.0 or next generation of learning systems? And this is not like immediately obvious, because programming languages research is about abstractions, about symbolic, about deduction, about reasoning, about modularity, compositionality, things like this. A lot about symbolic, and we like guarantees. So there is not like an obvious match here between this kind of PO thinking and the messy world of learning, of deep learning. Now, something doesn't have to be obvious to be effective though, right? And what I think is the time is right to where this PO thinking, this thinking about these problems and adapting some of our techniques a little bit here and there, or maybe more than here and there, but still it's really going to be not just impacting it, but potentially driving solutions to some of these more fundamental problems, all right? And what I'm going to try to do today is to convince you of this. And for that, I'm going to consider a challenge. And this challenge is going to be about creating accurate and safe deep learning models. Okay, so that's a fundamental challenge. It's a very important challenge. It's a hard problem. Okay. Many of you have seen examples where deep learning models fail. They're quite unstable. So for instance, there was some work where it takes stop signs, puts stickers on it, and causes the model to misclassify to a 45-mile-per-hour sign, cause the car to crash potentially. It's a hard problem. But it is also a broad problem, because as we'll see today, it's not just going to be about safety and robustness. We're going to touch a little bit on these issues with background knowledge, reducing the number of label data that we need, and so on and so forth. And it's a technically rich problem, because what I'll talk about today is a bunch of technical concepts like optimization, like abstractions, convex sets, like projections, taking a point like this red point and finding the nearest point inside the region, like logic. And we'll see how these concepts combine potentially in ways that maybe you haven't seen quite like this before. So it's a very rich problem space that is somewhat near to where we are. Okay? So if you want to address the global challenge, notice I'm not saying let's verify models. I'm just saying let's create state-of-the-art accurate and safe model for some definition of safety. You need to consider at least 4 research directions. So at least 4. This is attacks, which is trying to break the model, like testing, verification, trying to prove properties about the model, empirical defenses, which try to train or synthesize a model that is less susceptible to attacks, harder to break, and provable defenses, which are training techniques, a class of training techniques which try to train a model that is much more amenable to verification. You can prove more things. So the first 2 are about analysis, broadly speaking. The next 2 are about combining analysis with training in some way. Okay? And what I should say here is that there are many communities working on these problems. Just on attacks alone, there are thousands of papers a year. And different communities work on them. Rarely somebody works on them together. But I think to make progress, we need to look at them together, as a whole, and see what happens. So what I will do next is the following. I'm going to go over each of these 4 points, each of these 4 research directions, and I'm going to highlight what I think is state-of-the-art, what is interesting for us, and open problems in each of them that we can work on. So let's start with attacks. So let's take a point, let's take an image, like image 8 here. And our goal will be to perturb this image in some way, maybe rotate it, flip it, add brightness to it, darken it. Some transformations that to human perception, like to a 3-year-old child, they would all classify it to 8, but a machine perception, like a deep model, would misclassify it to something else, maybe to 7. Okay. So let's define it a bit more formally. So we're going to be given a model M. We're going to be given an input point like our image X, and we're going to be given a region S of X around our point. This region S of X that you see around the point like the image 8 could be defined in many ways. Oftentimes it's defined based on some norm. The distance is some norm, maybe an L infinity norm, L0 norm, L1 norm. It not so important for our purposes here. The L infinity norm, essentially you can think of it as taking an image, taking the pixels in that image and replacing each pixel with an interval which captures by how much you can perturb the image. And so if you have a k-dimensional image with k pixels, you'd have a k-dimensional hyperrectangle. In 2 dimensions, it's a box. Okay. Some people argue that L infinity norms capture human perception most naturally. There remains to be seen, not clear. And of course, there's other ways to generate the regions of interest that we'll talk about later. So what is the objective? The objective is to find the point inside the region, which the model classifies to some other label than the original label T. Okay? And this problem is typically solved via optimization of some kind. Okay? There are many, many papers. They mostly differ on how the region is defined and how the optimization problem is defined. But more or less, it's about optimization. You're trying to use gradient descent-like techniques to search inside the region to maximize some loss function, basically driving finding a point that drives the model away from the label T, meaning it is less likely to classify the point to the label. So try to drive it to classify it to something else, and that's it. So there are many, many variants of these different optimization problems, different regions, but more or less it's this. So what's the fundamental problem here from a programming language perspective? That doesn't seem like there is some connection here, but there is. So these optimizers typically, these gradient descent optimizers, they have to search inside the region. And when they search inside the region, they may step out of the region. When you step out of the region, you got to get back into the region. And if you want to get back into the region, this is called projection, to find the nearest point in the region. And so efficient projection algorithms are key because you do this over and over again, both during attacks and during training. So problem number one, efficient projections. Hyperrectangles in two dimensions are boxes. And so the complexity for projecting a point, like the red point, onto this hyperrectangle is linear. You just go over the point and clip the dimensions. Now let's suppose that I give you another convex shape, another set, like an octagon, for instance. What would the complexity be to project the point onto the octagon? What about some pentagon or zonotope or some other subpolyhedral domain? You know, this is not really studied that well. And if you pop up a little bit, you'd know that in abstract interpretation in programming languages, that's technique that came up here in abstract interpretation, you know, in Popo, there have been 45 years of numerical abstract domains by people like Patrick Cossot, by Francesco Ranzato, by Antoine Minet, by Francesco Logoso, and many others, which have constructed domains, abstractions, convex relaxations usually of some kind, where the abstract transformers trade off scalability for precision. And so the fundamental question is there such a hierarchy for projections? Think about this. Problem number two. There's thousands of works on attacks, many, okay? And they all output concrete points, like the image 8 rotated and now misclassified to 7. So is there such a thing as a symbolic attack where I don't just output a point, but I'm outputting a region where everything inside this region is misclassified? So something like a symbolic attack. There are many uses of this, from explainability, interpretability, understanding what is going on. Upstream tasks which would never produce this region because otherwise the network would get into a bad state. Training, and so on and so forth. There's very little work on this problem. So, you know, if you want to visualize it, you'd take not a single point here, x prime, but a region of them, maybe represented in some convex shape, where everything is misclassified. This is similar to precondition inference. Not quite, but similar. So you see, even in attacks, there are ways in which convexity, in which symbolicness interacts with optimizations that is fairly clean and really hasn't been studied that much, I think. So that's what I wanted to tell you about attacks. You know, some interesting problem that I've observed in our work in this space. I want to shift to verification now, which is the task of proving that there are no attacks, right, that perturb the point to be misclassified to something else. So if you come back to our example here, and we take the point 8, the image 8, and we can do all kinds of perturbation to it, you know, we're going to try to prove that no matter how I perturb the image, you know, all of these points are going to be classified to 8. If I have incomplete verifiers, or if the property doesn't hold, I may get false positive. I may not be able to prove it. So, you know, I may fail, and you know, this is not guaranteed in general that I'll be able to prove it. The challenge here with verification is that you can't really enumerate all the possible perturbations. You know, you have 784 pixels, let's say, each has 2 values. That's 2 to the 784. That's not going to work. And standard solvers like SMT solvers and mixed integer linear programming solvers, they also don't scale due to the particular scale to the size of models that we care about, due to the particular nonlinearities that arise in these deep models. And so we know from programming languages that what you need to do if your analysis doesn't scale is you need to employ some form of abstraction if you want to automate the process. And so we had this insight a couple years ago, which, you know, put in that way is kind of obvious. It basically says deep models are affine transforms and restricted kind of nonlinearities. And abstract interpretation has had, you know, 40 years of numerical domains. why don't you just merge the two together? And which is what we did in this framework called AI2, which gives you a generic construction to take advances in numerical domains and apply them to this problem of certification of deep models of neural nets. All right? So how does it work? It works exactly as you would expect. You have a region, this perturbation region there, some precondition, and this is described by some logical formula. Here it's a zonotop, doesn't have to be, could be something else, some other symbolic constraint. And then what you do is what the framework does is it tells you what are the abstract transformers, right? How do you propagate, this shape through a layer, like the affine layer, or through like a ReLU activation layer or some other layer. So it gives you this construction. And the way it does it is by taking this layer and breaking it down into very small pieces and applying the standard transformers. All right. And so you would run this through, and you'd get these convex shapes, or maybe a set of convex shapes, and they would capture an over approximation of all the possible values that can happen after each layer. You'd get the final shape, and then you can prove the properties that you care about, some safety property that you care about. So it was the framework. This, I think, excited, even though Patrick also doesn't love neural networks, we somehow married him with neural networks. What can you do? That's how life is. But this I think is kind of obvious construction, I would say. Excited, I think, some people to start looking at this problem. And even without this work, people were looking at this problem, but just excite a bit more people. And so what happened from here on? It looks like the problem is solved. This kind of framework scales more than prior work did to larger networks, to larger models, but still far from enough to handle realistic models. And so what people did, they said, listen, let's, instead of having this generic framework, let's just define custom transformers for these arrows, for each of the layers. And so over the last year and a half, there has been a lot of work in the machine learning community, almost nothing in the programming language community, by the way, except some papers here and there, on defining what I would say are abstract transformers of various convex shapes in order to verify properties. And they are not systematized somehow. There is a lot of them expressed in a very different way. So if you try to read the papers, you're going to get confused, likely. So I'm going to try to explain them to you in a way where you'll not be confused. And then you'll see why they got confused. Okay? You'll see why they got confused and why they made some mistakes. So by and large body of this work, including some of the work we did, can be summarized as just a single neuron abstract transformer. That's it. So what this says is the following. You have two neurons, x1 and x2, here. Maybe you're in the middle of the network somewhere. And now there is some symbolic information associated with this x1 and x2, some constraints which define a convex region, this thing in blue. And then what your job is to propagate these shapes to the next, through the layer, in this case a ReLU rectilinear activation layer, which basically takes the max of x1 and the max of x2 and sets y1 and y2 appropriately, of 0 on x1 and 0 on x2. And so what they do at a high level is that they just say, listen, let's compute the constraints for y1 by just looking at x1 and compute the constraints of y2 by just looking at x2. Okay, why am I not getting a box here? It's 2 dimensions. Because x1 and x2 constraints are referring to some shared variables, z1, z2, and when you propagate it, some of this transitive dependency remain, and you get something which is not a box, but maybe some other shape here. But the key thing is that y1 only depends on x1 when you do the pass, and y2 only depends on x2, and that's it. Okay? There are many instances of this. So let me show you some of those. So let's take the case, let's show the ReLU activation function. The max y is equal to max of 0 and x. X is on the horizontal axis, y in the vertical. And these Lx and Ux bounds that you see are just the interval concretizations of the symbolic constraints associated with x. So it gives you some potential ranges on x. This is a non-convex region. The first thing you can do is what Echlers did in paper 3 years ago or so, where he said, look, let's find the tightest convex region that approximates these points. And this is the triangle. That's referred to as the triangle approximation. This is even before AI2. Now, the triangle approximation doesn't really scale that well as well. You need free constraints to describe the shape, and when you propagate down, we're not going to get into this. You have to deal with the affine transforms and so on and so forth. And so that triggered many works, including us and others, to start to look at other convex approximations of the triangle in the middle. So here is one of them, like a zonotop. Here is another one that appeared at Popo last year, deep poly, and there is 2 variants of this, you know. And there is a few interesting things that you see here. So 3 points. Point number 1, keep that in mind. I have shown you the case for LU where the x is crossing the boundary from 0, less than 0, and greater than 0. For scalability of verification, this is one of the most important points. The more of these crossing values you have, the slower your verification is. If x is just positive or negative, the verification is much faster. So it's not just about the size of the network. A second thing that you can notice, more high-level point, is that many of these works are actually appearing in machine learning conferences, ICML and URIPS and others. And I don't know where the programming language people are. This is like a pure static analysis problem, pure program analysis problem, like numerical abstractions at its core. Okay. And there are many of these things. I'm not showing you other approximations which lose even more precision than here. One thing you'll see immediately that there is no best transformer, right? Because these are not closed on the intersection. So for instance, here, if you look at the zonotop, you can actually move the slope around and obtain other approximations. Now, what is going on? There were so many of these that it triggered these guys at last year New Rips to write a paper where they conjecture and they say, essentially, it's called a convex relaxation barrier to verification of neural nets. And what it says is you cannot do better than triangle at a high level. Okay? You cannot do better than triangle. And to some degree, it's true. These are all approximating the triangle. But this is only true if you're looking at the single neuron abstract transformer case, this kind of view that I presented to you. If you're looking at treating x1 and x2 together, you can get more precise results, so you can break this barrier. So we did that. We wrote a paper in the same conference that say beyond the single neuron convex barrier. So the 2 papers are side by side. Why does the confusion happen? Because, you know, and the paper is nice actually because it is looking at comparing the different relaxations. Probably should just not have been called the barrier, but it was trying to compare all these relaxations somehow. So in this framework that we introduced, you can actually consider x1 and x2 together. So if you use the best triangle approximation and just compute y1 as a function of, you know, x1 and y2 as a function of x2, then you would get the following shape that's up there. This is the best you can get. If you use the framework where you are considering x1 and x2 together, you can get a tighter approximation. Now, okay, it breaks the barrier, the so-called barrier, but, you know, it is actually slower than the triangle. So what's the use? Now it's slower than the triangle. We try to be faster than the triangle. Well, the use is that you can apply this kind of, you know, framework where you are treating some dependencies together and some not. Those of you who are familiar with decomposition, they will recognize this idea. And selectively you can apply it, and then selectively get a lot more precision of the analysis while keeping the scalability as much as the single neuron abstract transformers. So this is something that Gagandeep Singh did. He's actually on the market this year. So there we go. Right? So that's quite interesting. There's so much more work you can do from here. Because which neurons you select, x1 and x2, in order to define the transformer, is completely unclear. And the transformers are right now fairly slow. This optimal transformer I'm showing you at the bottom. Okay. So in terms of verification, you know, this was implemented. All of this you know, convex domains were implemented in this framework we call a run, which takes a neural network, takes a precondition like this M-infinity boxes or something else, and a property, and it tries to verify it. One interesting point here is that, an interesting point here that I think is quite unexplored is the fact that the convex relaxations can actually speed up your complete verifiers. So if you use them together, you can actually get faster complete verifiers. Now, so just so that you don't get the idea that we're just taking an image and just putting intervals around the pixels, you can produce these regions, these preconditions, in a different way. So for instance, if you want to solve the problem of geometric certification, right, where you want to prove that no matter how you rotate an image by some angle, you get the same classification, you can do the following. You can take the rotation, let's say, between 0 and 30 degrees, and then produce a convex region. And this typically rotation is combined with some interpolation, like bilinear or bicubic interpolation, which is continuous, so you cannot enumerate. And you can process the rotation code or the transformation code with this interpolation and produce a region which which over-approximates all the possible images that you can get from the rotation. And then you can give this to the framework like a run or some other framework. Okay? So let me give you some thoughts now, my thoughts on neural network verification. Because people like verification. We like verification. We really like verification. We do. So what has happened so far, roughly? So far, most of the specifications that have been considered have been norm-based, mostly L infinity norms of some kind, a little bit of L0, L1, but these kind of things. There's very little in terms of semantic specifications, like rotations, like audio processing, some deeper pipelines. We really haven't investigated much of this. So we must do that, because specifications drive abstractions. You cannot have abstractions, without specifications. As far as the abstractions themselves, there is a bunch of these single neuron convex relaxations, these single neuron abstractions. But many more custom abstractions are possible in the style of this k-array framework that I showed you. The integration with complete methods like MILP solvers is basically not investigated yet. It's pretty open. Right now, the integration is so basic that you can scale this much further. So I believe we need to work on kind of a neural network solver specifically for verification that has not been done. Now, in terms of network types, so far mostly classification, a bit of regression, but really we haven't looked at generative models, for instance, much, or recurrent networks, or specific domains like object detection, financial predictions, proving properties there. And one nice thing that tends to happen when you look at different kinds of networks is they have different kinds of functions that make up those networks, those models. And the interesting thing is that it allows you to come up with abstract transformers for compositions of them. So every time you look at a new architecture, you almost for sure have some new kind of convex relaxation that is better than what I'm showing you here. Likely it's going to be the case. So finally, the touchy subject of network sizes. So the first thing that people ask is like, okay, what is happening? How big networks can you handle? This question is underspecified because it depends on how many crossing radius you have, where the x is between both positive and negative. But by and large, at a high level, we are still at the small to medium-sized networks. And I think that we will not be able to make fundamental progress unless we can consider training in some way, which we will do in the rest of the lecture. Okay? So overall, I'd say we're still far away from verifying realistic properties for solving our challenge, the challenge that we posed from the beginning. We're not there yet. There's a lot more work that needs to be done along the lines that I mentioned here. Okay, so attacks, verification, mostly in the analysis space. Now, let's switch a little bit towards training. So what we're going to do now is we're going to look at this something called empirical defenses. And these are specific training mechanisms that produce a network, a model, which is less susceptible to attacks. It's harder to break it. Okay? So let's see what is going on here. So here is standard learning. Standard machine learning says, find the model. I apologize for the math a little bit, but just please carry through and it will be fine. So you want to find the model defined by some parameters, which essentially minimizes the expected loss. Okay. This expected loss is approximated by the empirical risk. You just evaluate the loss function on the data set, training data, and you average out. Now, side by side, let's look at side by side at a particular kind of empirical defense called adversarial training. And what you see in the two formulations, everything is the same, except in the adversarial training, which was introduced by Alexander Madry a couple years ago, is that what you're trying to minimize is the expected worst case behavior of the loss. So you take a point in the data, if you like, you find in that region that we have S of X, you find points that make the loss behave badly, and then you try to find parameters that minimize this bad effect. Okay? So these are the two things side by side. And if you look at the line, there's many people working on this adversarial training. And if you look at what is going on right now, you see that adversarial training, this is a common theme, can reduce accuracy, reduce the standard accuracy, but makes the thing more robust, makes the network more robust. So fewer things classify correctly, but more of these points that classify correctly, more of those images are actually robust. They're harder to break, experimentally speaking. So this has triggered people to study, how to improve these results. And what they say is, you may need more data, bigger networks, and so on and so forth. And there's one very interesting paper from Percy Liang's group at the bottom here, which says that, look, we have the labeled data. We want to improve the results. Now let's take unlabeled data. And for this unlabeled data, let's give it a specification that all of these images in the unlabeled data should be robust. I don't know what their label should be, but they should be robust. Okay. And this improves the results. So coming back to the adversarial training, what you see is that this looks like a particular instantiation to where you are trying to enforce a property, which is robustness, one particular property, and you're training the network to enforce this property. So from a PL perspective, programming language perspective, what is the question that you would ask? You'd say, let's generalize it to arbitrary properties, arbitrary logical properties, right? This is what we investigated last year in ICML. So everything, the whole pipeline stays the same, except that now you can provide the logical properties where robustness is a special case. So for instance, you may give the property like, if you're misclassifying a car, misclassify to a truck, not to a dog, for instance. Okay. You give some background knowledge. So back to this point about background knowledge. Okay. And how does it work, technically speaking? Well, you take the property that in some logical fragment, and then you are going to define a translation from that logical property formula to a loss function. And then you're going to define an optimization problem, which essentially is going to be the adversarial training optimization problem, slightly lifted. Let me give you an idea how this works. One nice point about this is that these background priors, again, look like, unexpectedly so, they reduce the amount of needed label data. Okay, so you reduce the number of examples that you need by giving these properties. So how does the translation work and what does it do? So here is an octagonal shape, some property phi, and a bunch of intersecting lines in 2 dimensions, 2 variable pair inequality, so you get an octagon. And when you translate that logical formula into a loss function, the theorem is such that where the points where the formula is satisfiable are the points where the loss is 0. And the points where the loss is 0 is where the formula is satisfiable. So you have an if and only if theorem here in this particular translation that we have. And this allows you to have at least some understanding how you're trying to enforce background properties into the network. This looks at a high level that it may solve the problem. So what is the issue? The issue is that there are many translations, which this paper didn't investigate. There are many translations that satisfies this theorem, and some produce much easier optimization problems. In fact, what you should be thinking about is synthesizing those translations, because they depend on the model, they depend on the property, they depend on the data. Okay, so that's one thing. A second point is that if you have logic, you have implication, you have abstraction of the formula. So what if you now take the formula, you abstract it a bit, you translate that thing into a loss, enforce it, and maybe you'll be lucky and you'll find the point in the original one, in the original formula. So how would you integrate this abstraction, refinement, abstraction coarsening in this logic to loss kind of matter? This has not been done at all, has not been studied. So keep the theme in mind that this is a repeatable problem of defining simpler optimization problems. Here it comes up again, just like it comes up also in the attacks that we mentioned before. So this gives you a little bit of an idea about empirical defenses, adversarial training, which tries to make the model less susceptible to attacks, more robust, loses accuracy. We still cannot fully figure out why. This can be generalized to logical properties, but then there are problems with the translation. You can make a very complicated optimization problems, which theoretically should be fine, but the optimizer cannot find solutions. So this, I think, is a very interesting direction for us. And now finally, we're getting to the last point, which incorporates all the other points, advances from all the other points. And this is something called provable defenses, right? Meaning you're going to train the network in a way where it is more provable. So more points, more images will be provably robust, or whatever properties is that you care to prove. So let's see how we think about this problem. If I have abstract interpretation in the forward pass, and I'm propagating these convex shapes, I want to keep all these advances in my pocket. I don't want to now start inventing some specialized training scheme. So I keep this exactly as I showed you in the verification. Nothing changes. What you do is exactly the same. Take the shape, take the precondition, push it through, get to the end. And now what you say is the following. You say, look, my goal is to find ways in which I can change these layers, change the weights associated with the network, these parameters, so that the final shape that I get is made smaller, intuitively. So imagine I have a program has parameters, and I'm trying to figure out parameters that when I analyze this program with some abstract interpreter, the convex shape at the end is as tight as possible. It's a similar problem. It reminds me of a paper that we did actually at Popo 10 years ago called Abstraction Guided Synthesis. There is some relation to this. So essentially, you're going to backpropagate through the abstract interpretation transformers instead of through the concrete transformers. And that's it. There is nothing more to it. If you look at the optimization problem, it looks very similar to the adversarial training optimization problem, except that you do not try to find a counterexample in the beginning, how you transform the image to make the loss behave badly. You take your convex shape, you push it through, you get a shape at the end, and once you get a shape at the end, you try to find the point in that shape, Z, which behaves badly with respect to the loss. And this is it. This is all that this says. So M star here is just the abstract interpretation of the model going forward, starting from the region Sx. That's it. Differentiable abstract interpretation going forward. So this also kind of got popular. People started experimenting with this idea, and there were many improvements since the ICML 18 paper. Many people, try different tweaks. We tried different tweaks. We try to get the results higher, try to get the accuracy higher, try to get the probability higher. DeepMind picked up on this idea, and they said, let's make it scale, let's make it better. Great. And so what they did is they considered the case where you're only propagating boxes, intervals going forward. Very simple propagation, just boxes, because it's very fast. Single neuron abstract transformer, again, just box. So these are all like hyperrectangles in the middle. And they did some other improvements, like annealing the input, and this is probably not so important, but it improves the results. We also did some work, other people did some work, and but still following fundamentally this optimization problem, this thing here. Okay, so what are the results? Because this is ultimately what we want. We want a model that is accurate and is safe, that I can prove things about it, Well, these are the best results, and I was being even generous. I took the CFAR10 dataset. This is one of the datasets where everyone evaluates their technique on. 10 means 10 labels. We picked a relatively small L infinity region, so a relatively small hyperrectangle around each point, 2 out of 255. And we took the results from all the papers on this problem to see what they got. So the best accuracy that you get on the test set is 70%. And the best certified robustness that you get, meaning what % of the points that evaluate that are accurate, you are able to prove robust, that there's absolutely no perturbation that can mess up the network. It was 53.9%. So just to give you in context where we are, the accuracy for CFAR10, the best one is 99%. So you see, this is off by 30% accuracy. This is insane. What are you doing? Like what's going on? And there is something even more disturbing here. That better abstraction, this is completely counterintuitive from a programming language perspective. That better abstractions going forward, I don't pick box, I pick zonotop or some restricted polyhedra, going forward, do not bring better results. If you tell this to a programming language person, they will think you are crazy. How can this be? You know. And we spent so much time tweaking this thing, getting slightly higher results, but didn't get anywhere. So we got into this situation of like, now what? And this is not like verification where you can, you know, tweak the abstraction a bit, do something, and then improve the results a bit. This you have to wait for this gradient descent to produce some weights. God knows what it's doing. You know, super frustrating. And I can understand why people are afraid of training. You know, I'm also afraid, but what can I do? You know, and so what it told us here is that we need some conceptual advances. We cannot keep running GPUs and TPUs and just hoping and praying that something works, you know, especially not in an academic lab. So here's the first fundamental question. It's a basic question. So applying PL thinking, let's say. First question, stop these experiments and think, is there a network even which has perfect accuracy, kind of like the universal approximation theorem, can approximate a continuous function arbitrary clause, such that when I push box through it, I get perfect, I never lose precision. So this would be the case where if I give you a program and I analyze this program with an SMT solver, and I analyze the same program with box, I get the same result. Is there such a program even? You know, this won't answer our problems fully, but at least it will tell us, you know, this propagating forward of the box is something that's part of the method. You know, we must know, because if the answer to this is no, then we really have a deeper problem. And so there is an upcoming work that Maximilian did. It's a student who came to us from ETH Physics, who is interested in the more theoretical aspects, I would say. And he proved the universal approximation theorem with certified network. Essentially, the answer is yes. That's an upcoming paper, like in May or something. So this answers some kind of existing question, but the answer is still, it's still impractical. We cannot just take this construction and use it. So a lot more work is needed, and I encourage you to look at this. It's a very interesting development because the constructions that he gives is dependent on the kind of domains you're using. If you use box, it's one construction. If you use zonotop, it's going to be another construction. This has not even been explored yet. If you're propagating L infinity boxes, these hyperrectangles, it's one construction. If it's another specification, it's another construction. So this is not quite explored so much. So that was the first thing we asked, but this doesn't help us in getting higher numbers. Question number 2, this is the most frustrating question. Why are better abstraction not producing more provable networks? This is infuriating from a programming language perspective, you know. And here's a hypothesis. Here is our hypothesis. He also wants to hear, I don't know what they're doing, but so the hypothesis is that more complex abstractions produce a more difficult optimization problem. Why is this? Because imagine you have weights in the network or parameters in your program. And what you're trying to do is to tweak these parameters with gradient descent or some other way so that they induce different convex shapes. And these different convex shapes are described themselves by many parameters, like polyhedra, for instance, the coefficients of the polyhedra. So you're somehow indirectly trying to change the weights of the network to induce some smaller convex shapes. And so this is just very hard. It's just a complicated optimization problem, and this is not what happens with normal machine learning. So it's maybe not surprising that you cannot get good answers, good results with more precise abstractions. This is the hypothesis. We don't fully know if this is true. This hasn't been studied that much. And so what you need fundamentally is a training method that is a bit different than the one I showed you, similar in spirit, but that has produces a simpler optimization problem. Okay. To see what the simpler optimization problem would look like, we need to put side by side to look at the extreme points. Well, I presented to you in this particular way so that you can see it very easily. So this was the adversarial training, this empirical defense. And what this was trying to do is it was trying to find a point inside the region which makes the loss behave badly, enlarges it. So works in the beginning. The provable training that we looked at with the DFI style, what does it do? It finds points at the end of the analysis. So one works in the beginning and one works at the end. And so this one here with adversarial training tends to produce good accuracy. Not as good as baseline training, maybe 10%, 15% off, but certainly much better than that one on the right. It has worse verifiability than the one on the right, but it's much easier optimization problem. You know, and the one on the right has bad accuracy, the 70% that we showed, but better verifiability. You can prove more things robust, but it's a much harder optimization problem. So now when you see them side by side, one on the left, one on the right, what are you thinking? You're thinking, what's in the middle? Right? There's nothing else to be thinking about. What else would you be thinking about? Definitely not breakfast. Think about optimization, my friends. So, and so there's this work that we did after this insight, which I think is a new way to do provable training. And this is an oral at ICLR, oral paper ICLR. This year with Mislav, another great ETH student. And so the idea is super simple. It is basically says, use your analysis, pick your domains, whatever, boxes, zonotopes, I don't care. Pick your preconditions, whatever region you have, maybe from geometric perturbations, maybe from L infinity boxes, doesn't matter. Push it through once. This is the first layer. Get a region here, the dark blue one. And then what you want to do now is you want to look at that dark blue region and you want to find a point inside the dark blue region which makes the loss behave bad. So if I find the point, I just run the network layers H2 and H3 and I get some value for the loss. And in a sense what I have done is I have frozen H1. I don't touch H1 anymore, the hidden layer H1. I just touch H2 and H3, just these parameters. And so I just pick a point and I just do normal adversarial training in the middle of the network. That's it. It's a much simpler optimization problem. I don't have to touch H1, I freeze H1. And once I'm done with training with respect to the dark blue box, I move on, I go to the next one, and I repeat the same thing. What do you see here again? You see that you need to find points inside the convex region. Where did we see this before? We saw it when we were talking about attacks. We need to find points inside the convex region, and this convex region may be zonotop, maybe box, maybe God knows what. Okay? Once you find this point, you can just push it through and do your normal adversarial training. So again, projections. Again, projections. And because we are not so good at projections right now, we don't understand it so well, we only did this work for zonotops, where we can reduce it to box projections. But the scheme, you can describe it in one page. So you don't need all these hundreds of tweaks and all this kind of stuff people are looking at, that just simplify the optimization problem in this clean way. So that's it. So here are the numbers you get with this scheme, So before, the best numbers were taken from two different papers even, 70% accuracy, 53.9% certified robustness. Now what you get with this scheme, and this is without some other optimizations you can do, you get 78.8% accuracy and 58.1% certified robustness. So you can prove more, it's more accurate. It is still not there. We are still not there. It is still low. This should be in the 95% range, at least 90% range. But at least for the first time, you can show that more precise abstractions, you have an optimization procedure where more precise abstraction help your training, robust training, but more precise abstractions also mean more complicated projections. But we don't know how to do too complicated projections right now. So we're still not quite there yet. Okay. So I looked at, we talked about this general problem of building safe and accurate models. We looked at attacks, verification, empirical defenses, provable defenses, some advancements there, some, hopefully you got some interesting problems out of it. Now this is a lecture here. At ETH we have a whole course on this that's been going for the last 3 years. That's attended by about, between 200 and 300 graduate students from mathematics, physics, statistics, and so on and so forth. And so we go in a lot of these topics in a lot more detail. And one thing I'm thinking we'll do over the next month or two, oh gosh, I'm on record, that's bad, is that we'll release all these slides and exercises, because this is not a seminar, this is really a full-blown course on these topics. Yeah. Okay. So in summary, popping up, I think, the time is right that there's a bunch of problems with deep learning right now. I think this PL style thinking can help in, I hope I convinced you of this, to address some of these problems. We looked at this problem of, creating safe and accurate models, state-of-the-art models. We are far from solving this challenge. It won't be solved this year, and next year it will be at least a few years until we make substantial progress. There are at least 4 directions you need to look at: attacks, verification, empirical training, and provable training. I think if people with the background that you have, it shouldn't be, it's much easier for you to get into the training than I think vice versa, if you just know the training into all this abstraction and symbolic reasoning. I outlined a bunch of problems that I think are interesting to look forward. And, I want to thank, this is all work with collaborators. Everything is, I last looked at the DBOP and I saw more than 100 collaborators. We're really just doing incremental work on top of huge amount of research that's been done here in the machine learning community, mostly improving existing results. Everything is really incremental work in my eyes. So I want to thank all my collaborators. Without them, none of this research would be possible at all. Especially want to thank my group at ETH Zurich. It's just some fantastic students in this group. I really enjoy working with them. And I'm going to end with a question: can programming language researchers impact next generation learning systems? You can answer. So thank you.
Questions? Let me start over here.
Thanks, Martin. That was a tremendous and really informative keynote. Thank you. So I was wondering about this S variable that defines the nearby points in the region. It seemed that all of the verification and robustness results were with respect to a particular S. And I guess I'm wondering how you pick the S, and how do you know that you've got an S that's kind of big enough but not too big? I was thinking with the stop sign example you had right at the start, if you put enough white tape on your stop sign, it's no longer a stop sign. So yeah, how do you pick S?
Good question. Nobody knows, my friend. Nobody knows, really. The reality is the following. What's happening right now, I think, is that we're mostly looking at these norm-based perturbations. This 2 out of 255, 8 out of 255 is the biggest one that has been considered. You look at the images, you make this change and you suddenly start seeing that they start looking bad. You reduce the norm a bit of it. I think it's fairly empirical. We don't have a good understanding how to pick it. But the interesting bit here is the following, that even with the current norms and current perturbation regions SX, we're still using them to improve the abstractions and relaxations that we have. We are still not to the point where we need to worry so much about how to pick the S. I think we'll get to that. For instance, when we started looking at vector field-based geometric transformations, there you start needing to define notions of norms. How do you define that 2 points are, you did a rotation and whatnot, are close to each other? You're starting seeing this problem creep in. It's a very good point, how to define the S. We're probably still not there, I would say, for at least a year. Yeah. Good question.
Okay, one question from Slido. You talked about attacks and blah, blah, blah. What about making it all more explainable?
making it more explainable. Yes. You know. So, you know, this thing I talk about, the symbolic adversarial examples, I think this is pushing something in that direction. One interesting point about explainability is we're going to diverge now. We're going to diverge, but we have to diverge. One thing we have found is that you know, there is standard works which take the deep learning model and they start to try to learn decision trees or whatnot, or some logical formulas. I think this doesn't quite make it more explainable. But one thing that we have found, and I think that's an interesting direction, is when you do the provable training, when you do this kind of adversarial training, what is the effect on the explainability of the model? So take all the methods for explaining the networks. Pick every method that you know. It's done based on baseline training. Now do adversarial training, do provable training, look at the explainability. I bet it's going to be more explainable for the reason that you have much fewer number of crossing values. So I think that's an interesting question, immediate direction.
So there is some work from Alexander Madry's group where they say that robustness and accuracy are maybe fundamentally at odds with each other. And so how does that sort of...
Like, are you talking about the adversarial, the bugs are features? Or?
Not that paper. I think before that they had a paper where they say...
yes, this is actually cited in one of the... I listed it, I think, in one of the slides. I think we don't know fully what the situation there is. How much accuracy can you get? We don't know yet fully. What we do know is that you need a lot more label data. What I think is going to happen is that you may be able to get to very good accuracy, but you need to give background priors. I don't think you'll just be able to get, if you just take the same data set, or famous last words, but if you just have a normal training data set like normally and just do normal baseline training, adversarial training, you're probably not going to get the same accuracy unless you give some, like Percy did, like some specifications. I think a lot is going to go to background priors. That's my hunch.
Yeah. So suppose you want to choose an S that's not L infinity norm, even let's say L2 norm, or corrupt some pixels or rotations.
Sure, yeah.
What kind of numerical abstract domains do you need to sort of pick different numerical abstract domains that work better with those regions?
Yeah. So abstractions depends on specs. Abstraction is about forgetting, and you cannot forget unless you know what the spec is. For instance, L2 norm is going to be quadratic. Convex domains that are quadratic. You're not going to do deep poly on that probably, right? You could, you're just not going to be very precise. For rotations and geometric transformations, what we found out was that if you take a geometric transformation like rotation, translation, or whatever, and you compose them or you don't compose them, it doesn't really matter. And if you try to propagate abstract transformers for this, you're not going to get good approximations. You need to investigate what people here have investigated, like Suresh Jagannathan. Oh God, I'm gonna butcher his name now. Suresh, I apologize. And other people like Madhusudan and UEC and others, is where you sample lots of points. And Alex Aiken worked on that, and Rahul Sharma and others. Like, I sample lots of points, and then I'm trying to fit planes to this set of points in order to approximate the region. That works better there. And by the way, that's a new way to infer invariance that hasn't been looked at for the normal neural nets verification.
Thank you. So you're focusing a lot here on how to improve the robustness of your networks, but could you say a bit how you would try to improve the privacy of the networks, like not be able to retrieve the initial training points, perhaps?
To prove the privacy of the network. Oh man. So this is, you need to define what that means. So privacy against maybe poisoning attacks, maybe what you're talking about is, are you talking defense against membership attacks or defending the training schemes? Yeah, I don't think that there has been, there's only recently some work where people are trying to use abstractions to approximate the training procedure. And then you can start proving properties like this, I think. Privacy, I mean, there's differential privacy too, like these kind of things, right? That also relates to fairness, to group fairness. There hasn't been, there's of course algorithms for differential private machine learning. I don't think that there has been much, in automated verification of this probabilistic notion of privacy. It hardly has been, even for the small algorithms that we have looked at in programming languages. There is some work from Justin Xu that is looked at verification there, but not for neural networks. I'm not so aware of this. We did some work on finding counterexample to differential privacy, but as far as probabilistic notions, not so much. I think if you have probabilistic notions, you need to do like probabilistic abstract interpretation. That's something that we didn't talk about. That has not been explored.
Hello, thanks for the nice talk. What if the tasks that you're targeting are natural language processing tasks, and where the input are string and it's kind of more discrete, and the perturbation can be insertion, deletion, character level insertion, deletion, substitutions, or transducer or whatever.
Yeah, good point. So there is work in ICLR. You can look it up on certifying transformers. How to do these days a work like this. Some of it I know that some of them do it on the embeddings, because you can define a space around the embeddings and verify this. And in the other ones, you just approximate these kind of things you're talking about with the replacements and whatnot with the box. And then you can propagate that through with some domain. I believe that's what that paper does. But there is work on this already. People have looked at that.
Many thanks to Martin.